I'm giving a talk called The Internet for SEO. I'm nothing but ambitious. When I think about the internet, this is kind of what goes into my head. We're home users of internet, we're work users, right? It kind of, as a user, we use a browser, and that's usually on one of our devices, either a phone or a desktop, and that's connected to a router, mostly wirelessly nowadays. That comes from our internet service provider that has access to this big network called the internet, where all these beautiful servers live, or the cloud, whatever you want. And on these servers, you have all these web pages that we're actually trying to see. And that's how we, 99% of the time, use the internet at home. But I'm not doing this talk to tell you how to use the internet when you're, at home. This is more a talk to help you communicate better with your developers. And I'm hoping you can take at least one thing back to them and facilitate that communication. I've been an in-house SEO for over 13 years and a technical SEO for the majority of that time. And I get to work closely with a lot of different teams, but I prefer working with developers, to be honest. And if I noticed or I learned something in 13 years of working with technical people is that even though we work over the internet, both teams, SEO and development, we tend to use different terminology, but we work with the website over the internet. So it's a bit weird, and I'm trying to gap that difference in terminology use between SEO and development, so then we can go to them and tell them what we need, and they can understand it clearly, or they can come to us, explain things, and we can understand it clearly. Because a lot of SEOs hate their developers, and they should be our best friends, because they know how to do stuff. So we have the SEO perspective, and a lot of us talk about crawlers and bots and render queues and indexing, because that's what we care about, right? We look at Google and what Google does. Developers talk more about IPs and servers and the cloud, and they care about browsers and how they request assets and how they render pages. And even though we use different words and we talk about different things, it's pretty much the same thing happening in the background. Because it's either Googlebot or it's a human who's requesting a web page over the internet. They have to use a client, which is a browser. Google uses Chrome, but as a headless version. You don't see it, but that doesn't mean it's not there. It's the same thing as if you're a user. And this client needs to send this request to a server. The server will try to create a response, send it back to the client, and then the client will render that response and show it to the user, or send the rendered version to Googlebot. It doesn't matter, the process is the same. Everything that happens on the right side happens over the network, and everything that happens on the left side actually happens in the browser or in the client, such as rendering. And this is where we get the notions of server side or client side. If it's information coming from the server to the client, it's server side. If it's information that the browser is rendering to show the user or Googlebot, then it's client side. So let's talk about this network, because that's where all the magic happens. Everything happening, as I said, between the client and the server is network activity. It happens over a network, and a network has hardware, physical components. And this is kind of how it looks. It's cables connecting countries and continents, bringing internet to everybody all around, because internet travels through cables, still, mostly. And you can see a cable pretty much like this, because it leaves from your browser at home through Wi-Fi, it gets in your internet service provider, it travels through cables and everything, it gets to a server on the network. But we have to realize that cables have a limited capacity of transmitting data. The bigger the cable, the more data you can transmit through it, but the narrower the cable, the less data you can transmit through it. So this is where we get bandwidth. If data travels through big cables that can get a lot of data at the same time, you're going to transmit more. But if your cables are quite small, as they tend to be as they get closer to home use, then you get slower internet connections because you can't get as much data through them. But it's not just how narrow a cable is, it's also about how long the cable is that data has to come through. If I'm trying to get data from the back of the room until here, it's probably going to be a millisecond or less. But if I'm trying to get the same data volume from the US here in Manchester, it's probably going to take about 20 milliseconds because that data has to travel through that cable across all that distance. And yes, we have fiber optics and data almost travels at the speed of light, but it still needs to travel and distances matter. So the further you are from a server, the longer it will take that data to come to you because of this distance called latency. But we do have CDNs, and you've heard Nick talk about them, and you should know a lot more about CDNs now than you ever did. And they simply work by adding a copy of the website closer to where users can be. So then when a user is requesting it, instead of going to the origin server, he just gets it from the server that's closer. So this way, reducing latency. Now, there's the software part of internet, and it's pretty much how it's working. There's two different big models of how the internet works, but this is the one we use mostly in our day-to-day at home and at work. It's the transfer control protocol or the internet protocol model. You might see it as 6 different levels, but I've simplified it. I'm going to talk about 4 of them. So this is pretty much how data travels through the internet, so then we all kind of get a consistent experience out of how the internet is being used. These different 4 layers are used for communication of this data. You have the application layer where you have different protocols, and you can think of protocols as rules. So for instance, the HTTP protocol that we use to get pages of the web is just a set of rules that says, if you want a page from the server, you have to do this. Or for instance, you get SMTP for email messages. Again, just a set of rules deciding how communication happens. You have a second layer where data is getting broken into smaller pieces so it can travel and travel more efficiently. You got the internet layer where an address is identified for where you want that data from. And then finally, all of this goes through the network interface and actually reaches a server in the cloud or wherever it might be to get that information for you. It's important to understand it travels both ways, so it goes from your message being decomposed, gets transmitted, and then the receiver has to compose it back again. And because I did mention the HTTP protocol, this is what we mostly use when we look at web pages, and it allows us to get pages that have information from different servers. So you can have images on one server, maybe a CDN, you can have videos from a different server and so on. And you can request all of these over the network and get that information to compose the page. Now, on the second layer, there was the TCP, it was TCP mentioned, which is how connections are made to servers. So it's, imagine this as a I don't know, like a tunnel of communication. So you have to open a tunnel between you and the server to be able to transmit what you want and get that response back. And we've been using HTTP 1.1 as the version of this protocol for, I don't know, 16 years, if not more. And the way this works is, if you want, let's say, 3 images from one server, you have to open a connection for each image in order for that image to come back. But if you want more than 8 images, you're out of luck because browsers have a limit. They can only do 6 to 8 connections at a time. So if you have a lot of resources, you can only do batches of 6 to 8. So that takes time because you have to wait for every batch to load until you get all the information you need. But lucky for us, in the past few years, you've been seeing more and more websites using HTTP2, and including Google can crawl as HTTP2 now, making crawl a bit more efficient, where if you get resources from one server, instead of opening a communication tunnel for every single resource, you just open one tunnel, and then everything comes through that tunnel at once, if it's coming from the same server. So it's important to have all your images in one place in this case, because they can all come at once. I'm not going to go into IPs too much because you should know what this is, but just look at the big number of addresses for IPv6, because we've already kind of reached IPv4. We don't have enough variations anymore, and I think with IPv6, well, it's going to be about 10 generations of people who will benefit from this before we might even think it's a problem again. Now, speaking of client-to-server communication, I keep saying, a request, a response, and I want to explain what a request is. And this is what your client sends to the server. It has a request line, a header, and a body, as you can see here. And I'm going to talk about the request line. It has a method. So for instance, if you're trying to get a web page, the method is get. It's that simple. It says the path of the web page as it's found on the server, and it includes the protocol. So indication of how would this communication happen for me to get this page. You have get, which we use mostly when we request something. You have methods like post. So for instance, you put in your password or username. You'd use a post method because you're now sending information to the server, not just requesting it. And then you have all these other types of methods that you might encounter online. The headers are very interesting. If you use developer tools, and you can use them in any browser, I'm using Chrome here, you can see headers for any single request. If you just go under your network tab, you pick on one of those requests. So it might be the HTML document of your page, or it might be an image or a video or anything else. And then you click on the headers tab, and you can see all that information. You have request headers. So this is coming from the client, and it says on this domain, I want you to give me this page found on this path using this set of rules. That's pretty much how you read it. And you can see there's a lot of other information there as well that might be of interest. But then you also have the response. So this is what the server sends back and says, here's your response. If you want to cache it, I'll allow you. So that's cache control. This response is coming from this server. In this case, it's Apache. And you might have headers that vary the response based on user agent. So you might be sending one response to Google and a different response to a user, which you shouldn't do because it's called cloning. Or you should do, but it depends. HTTP headers are magic because they allow you to do things for documents that don't have HTML behind them. So for instance, you have PDFs and you want to add a canonical back to an HTML page. You can, because a PDF doesn't allow meta robots in its HTML because it doesn't have any. So you use HTTP headers, and you can add canonicals for PDFs. You can even add canonicals for images, but just be aware, Google, for instance, doesn't look at that. You can add hreflangs if you have international PDFs. And you can even no-index them. Maybe you just don't want Google to keep crawling them, or you want to keep them out of the index, or whatever you want to do. You can handle a meta robots tag, but done through an HTTP header. Now, requests have timings, so they take a different time based on what they're doing. Whenever your browser is asking the server to send something, it will go through these steps. And I'm just going to go through the steps one by one. The app cache, the moment you're telling your browser, can I get this page? The browser is going to look in its memory and say, I got this page before, and I cached some resources from this page. So when I'm going to get it again now, I'm not going to get everything, because some stuff I already have. And this is why sometimes you get pages faster when you revisit them, because the information is already there. It doesn't have to travel through the network again. But if you do have to create that connection with the server to be able to bring information in, you need to first find out where the server lives. And when we request something, we say, oh, can you bring me this page from Wikipedia? But Wikipedia is not a server. 172.217.142.06 is a server. Actually, that's Google, not Wikipedia. But anyway, what the DNS does is associates a name that we use that's easier for us to use with an address on that big network. And that's how it identifies where a server lives and is able to connect to it. Once it finds that server based on the IP or its address, it needs to open this communication tunnel. It does complicated stuff. You don't need to go into detail if you're not interested in this. But once it manages to do this, it opens that communication tunnel. And then, because most websites nowadays are over HTTPS and they use a SSL certificate, you need to do an SSL handshake. So you need to make sure that connection, that tunnel of communication is absolutely secure and nobody can jump in and kind of hack your information as it's going through. So SSL handshakes nowadays kind of take 3 round trips around the network to establish that connection. But we're changing protocols, and you're going to notice new SSLs come as TLS 1.3. So that's the next generation that only needs to go twice around the network to establish the same very secure connection. So that means the timing for this to happen will be shorter. Again, developer tools, you can see the timings in the network tab. If you select any resource, you can see how it went through the network and how long it took. You'd see information like this. You have the connection part of it, so let's say I'm looking at an image coming from a different server and I'm trying to understand how fast is it coming. If it's queued or stalled, it means something else in the process of building that page has priority, and this image is not yet even requested from the server. But the moment it's requested, you're going to see the DNS lookup, the initial connection, which is that TCP communication channel I was talking about. You can see the SSL handshake. And once all of this has happened, the connection has been established, and then the request is actually being sent over the network. The request itself is just one line, so it's going to travel pretty fast. But once it hits your server, the server will have to actually build that request up. So if you're asking for a page that needs data from a database, the server will have to retrieve all of that, put the page together, and then send it back to you. The time it takes from that request reaching the server and the server sending you back the request is time to first byte. So if this is very slow, it means you need to improve your internal processes. But the good news is they're internal, so you could probably have a look at them. And then the time it takes from the server back to the client is the content download. If you have a very, very big file, that's going to be a long time. So you want to look into compression and other things to make that file smaller. Now, all of this happened in the network, but then all this information reaches the browser. So what happens there? As I said before, you as a user, you're going to go into your browser and say, I want this page, but then the browser breaks that request into smaller packets, sends it to the server puts together a response, and again breaks it into smaller packets so they can travel at the same time through the network, and then sends it back to the browser. The browser then does the rendering work, where it takes all these smaller things and puts them all together back into something that looks like one page. And it's improper to say browsers have hardware because they're software, but that's why we have the codes. So every browser will have a structure similar to this. The data persistence is actually where the cached resources are kept. And then we can talk about some of these things. The user interface is, of course, where you put addresses when you request pages. You have your back and forward buttons. You have your bookmark menu, and then you see the pages. So that's just the UI. The browser engine is kind of the software used that might be different from browser to browser. For me, it was funny to find out that Google and Opera actually use the same browser engine, because I never thought the two had anything in common, but yet here it is. The rendering engine is where all that information gets put together, and we're going to have a look at how that happens. Information comes back from the server in bytes, so that's very, very small packages of data. Those bytes get put together into characters, and then a series of characters can be seen as having meaning and becomes a token. So for instance, if we recognize an HTML tag, that's a token that means a start tag or an end tag for HTML. All these tokens get then combined in nodes, and all these nodes create the document object model, because you're downloading a document full of objects, and this is showing you how you should model them as you're trying to render. Same thing happens for CSS. So I'm not going to go into detail, but it's exactly the same thing. Comes as bytes, gets seen as characters, and so on. Now, if you put these two object models together, you get the render tree. This is literally a list of instructions that tells the browser, these are all the resources I need on the page in this order. This is the hierarchy I need. This is the CSS that goes on it. This is what goes in front or goes in the back. And it literally helps the browser understand how to put elements on a page. The JavaScript interpreter is very important, because nowadays we all use JavaScript to my sorrow, because I have to fix all the issues that JavaScript is causing. But a browser needs to be able to interpret JavaScript. So as it's going through the HTML document that it got from a server and trying to identify resources in it, in this parsing process, The moment it finds a script, it will stop parsing HTML, fetch that script, and then run it. And that's kind of how it works. But it's not good, because that means I'm delaying going through the entire HTML and discovering all other resources. And I need those to render the page. So this is going to slow down everything. Now the good thing is, things like third-party scripts, for instance, are loaded asynchronously. And this means that I'm not going to stop parsing HTML just because I found the script. I'm going to download it as I'm still parsing HTML, and I'm only going to stop that parsing the moment I need to execute that script. Or even better, some scripts can be deferred. They can wait until all of the HTML parsing has finished before they actually need to be executed. And if all these things sound complicated, they're not. Just go in the HTML of your page, identify a script tag, and see, do you have these words in there? Do you see async or defer next to any of your scripts? And if you don't, ask a developer why not. They may have a reason, but ask them. Right, so the browser will take the render tree, and it will figure out, based on that, the distance or placement of images, videos, text, everything you have on your page, based on how big the page is, and you will place them accordingly. You can see layouts and how everything was placed on the page. Again, developer tools. If you go under more tools, there's a rendering tab, and you can tick a box. And if any of the things that were initially put on your page had to move for any reason, creating a layout shift, which we know Google doesn't like, you will see it in your browser directly. So it's very good for identifying issues. Then the browser will start painting, and this is the moment when something actually appears on the screen for a user. Until now, nothing. User just waiting. You might have heard of perceived speed. This is because of this. You kind of want to pretend you're starting to do something so the user doesn't think they're just staring at a blank page. When it comes to painting, if that render tree is not done correctly, then you can get problems like this, where you get an image overlapping with text or things like that. But if it's done correctly, CSS will help the browser understand where to place text, where to place images, so everything has its place. And then there's this other step called compositing, which is the last step, which takes into consideration the size of the viewport or the size of the screen making the request. So if you're on a phone, you will have to recalculate how elements stand next to each other so they don't overlap. If you're on a desktop, that's probably easier because you have more real estate. If you think you have problems here and something doesn't look right, again, developer tools will help you analyze what the issue might be. Right, and this brings us to the critical rendering path. If any of you ever run a Lighthouse report, you see there's always an error saying that some JavaScript is blocking the critical rendering path. What that path is actually these steps that we discussed. Building the document object model, the CSSOM, creating the render tree, and then being able to lay out the information, start painting, and doing the compositing step. This needs to happen for a page to show in your browser. If anything else happens that makes these steps be delayed in any way, then your page will take longer to show to users. You can see this critical rendering path in developer tools based on those colors there. So you can see blue is HTML being parsed, and if you see blue being interrupted by yellow, that's JavaScript that's executing. The more yellow you see, the more problems you have, because you really want to go through your HTML as fast as you can. So now, how does it all fit in? Because you heard a lot of information, but where are the developers, right? So one thing that I learned by looking at this kind of stuff is how to optimize my crawl better. For instance, I was very obsessed with 404s, but they're part of the web, and they actually don't waste crawl that much. If you remember Nick talking about doing redirects on the edge, and he said redirects are not expensive to do because they only have a few bytes, because they only send headers. That's because, if you remember, the request has 3 different components. Redirects, 404s, 410s, they don't actually have a body. You're not downloading anything over the network. You're just getting that one message that has the headers and the request or the response line, and that's only a few kilobytes at most. So it's really not expensive for either doing SEO on the edge, but also for crawlers. So if a crawler finds a lot of redirects or 404s, it's not really going to affect your crawl budget that much. Now, of course, don't have 404s if they're causing UX problems. When it comes to Core Web Vitals, for instance, we all went crazy. We went to our developers and we said, oh my God, we have LCP issues, fix them. And developers were like, dude, what's LCP? Because these are metrics invented by Google, right? The developers don't come out of school knowing what Core Web Vitals are, or what's an LCP, or FDI, or anything like that. They have no idea. So then we go to them and we tell them, fix them, and they say, yeah, because they don't want to sound stupid. But then they're like, I don't have a week to study these things, I'm just going to do my other work. So SEO work never gets done. How about instead of doing that, you look at your critical rendering path, you look at your network timings, you identify places where you think this is taking too long. You can compare it to other pages on your site, you can compare it to similar pages for your competitors, and identify places where maybe your TCP handshake is taking too long. So you can take that back to a developer and say, hey, I'm looking at this very specific timing, can you tell me what's going on? Because it seems very big in comparison. They did study networking at school, and they do know what a TCP handshake is, and they do know where to look. So they're more likely to actually help you. If you speak language they actually understand. And it's just better for you as an SEO. You can conduct better audits. For me, it was such a discovery to find out all about headers, and you can bring that in your Screaming Frog information, and you can look at it. And to give you a quick example, let's say 90% of your users are returning users, and you're considering doing speed improvements, but you also see that all your pages are caching all resources. If they're returning visitors, they're going to get that cache from the browser. So in this case, it's not really a problem. It's going to be quite fast for them when they return. But if you see that 90% of your users are new users, they're not benefiting from that cache. That information needs to come from the server, so you do need to prioritize speed in this case, because they will be more affected. So hopefully you can go back and speak a bit of developer language. Don't call it that in front of them, they'll laugh at you. But I know from personal experience. But hopefully next time you want to ask them to help you solve something, you're going to use language that's going to be more familiar to them. Lots of resources if you want to learn more. I do recommend starting here, but the web is full of information. And that's it. Thank you very much.